We have here a problem involving working out the velocity of a particle after a force is applied to it in order to accelerate it. So it sounds to me a lot like a SUVAT problem. Let's begin by writing out the factors that we know. So s distance is equal to d. U, the initial velocity here, is equal to v0. V, the final velocity, well, that's what we want to find out. A, now we haven't been given an acceleration, but we do know that there's a force acting on a mass, so F divided by m will give us our acceleration, and T we don't know about, and actually we don't really care about. So which equation can we use here? Well, we know SU, V and A, so that sounds like a job for V squared equals U squared plus 2AS. So let's plug in the values we know here. So U squared is going to become V0 squared plus 2 times F over M times D, which means that V is going to be equal to the square root of all of that. So that's V0 squared plus 2FD over M. Now let's, before we go on to the next question, let's have a look at the situation we've been placed in now. So we have our particle accelerated from the first part of the question. So the particle leaves, travels in a straight line at the velocity that we determined in the previous question, before continuing into this region where it experiences a force perpendicular to its motion. In other words, it experiences circular motion. That is the definition of circular motion. The force accelerating it is perpendicular to its motion, which means if we were to continue this line here, it would circle round and would eventually hit the detector at some point here. Now, the centre of our circle, we can place a blob there. If this is the radius of our circle, then it follows that this distance here, from point to point, that's the diameter, or 2 times the radius. So we can say that the y that we're looking for here is actually just 2 times the radius of a circle, and actually we just have a circular motion problem. So the question is to derive an expression for the y coordinate where the particle is detected. So what is the y coordinate at this point here? So let's begin by writing out our equation for circular motion, which is F equals mv squared divided by r, and plugging in the values that we know. Okay, so the question tells us that F equals alpha v, where alpha is a constant that's greater than 0. It's just telling us that the force is proportional to the velocity. So alpha v equals our mass, which is still m, v squared divided by r. We can now cancel our v on that side and one of our v's on the other side to leave us with alpha equals mv upon r. Now remember, we need to find r and then ultimately y, so r equals mv over alpha, and if y equals 2r, then y equals 2mv divided by alpha. That is our answer. At first read through, this next part of the question looks terrifying. We've got lots of particles, they're travelling along the same path with speeds v, where those speeds are actually ranging between v1 and v2, so there's a big range of speeds, and the detector itself is not a single entity, but it's like a CCT. A CCT is what you'd find inside a digital camera. It has a finite number of very small pixels. The pixels here have a size delta y that are the same throughout the length of the detector. So what is the minimal spread of the speeds, delta v being greater than 0, such that v and v plus delta v is less than v2? are resolved by the detector. What a confusing way of writing it, but what it's saying here is that if some of the speeds are too close together, then therefore their y's, their distance along the detector, will be too close together as well and will land within the same pixel. So what we want to find out is what is the necessary minimum spread between different speeds such that the particles are guaranteed to land in different pixels. Let's begin by writing this out algebraically. Delta y here is the size of the pixel, so any two particles landing must at the absolute minimum be equal to, the gap between them must be equal to that delta y. So let's take one pixel to begin with, so 2mv divided by alpha. This was our y from the previous part of the question, and we want to find the difference between that y and the next smallest possible y that we can allow. So that would be 2m multiplied by v plus delta v. So this delta v is the important term here. This is what we're ultimately going to try and find, is the smallest increment of velocity that would still allow delta y to be large enough. Let's then rearrange this. All right, before we do that, let's expand out of the bracket. So delta y is going to be equal to 2m over alpha multiplied by v, take away v, take away delta v. We can now cancel our v's here, which leaves us with delta y equals minus 2m delta v divided by alpha, and we want to find delta v. We want to find what this smallest delta v is that will allow us to have a delta y large enough to see it on two separate pixels. So this will give us delta v equals delta y multiplied by minus alpha over 2m, which is going to be minus delta y alpha over 2m. And since delta v is a difference, it doesn't matter if we have positive or negative, so we can just say delta v must be equal to delta y alpha over 2m, equal to or larger than delta y alpha over 2m. Okay, for part D, before we do this, let's just remind ourselves of the journey of our particles. So the particles begin in an accelerator and they come out, they travel at a constant velocity before they enter this region here, causing them circular motion, at which point they get detected on our detector here. So let's have a think about the forces acting. While the particle is in the accelerator, there is a force acting on it here, which is small f as our force, and it's acting in the same direction as the particle is travelling. While it's in the circular motion region here, there is a force acting, big F, perpendicular to the direction of motion. In this region here, there's no forces acting at all. Remember from our definition of work done equals force times distance moved in the direction of that force. Now here's a problem. This force here is not acting in the direction in which the particle is moving. So therefore, actually, in this region here, the work done is 0. We already know the work done here is 0. It's travelling at a constant velocity. Therefore, the only work done on our particle is during this region here, because this is the only period in which the force is acting in the same direction as the motion. So we can say here that work done is equal to small f, which is the force in that region, multiplied by small d, which is the length of that region.